Hello, everyone. Welcome to 𝗬𝗏𝗃𝗃. Good morning, good afternoon, and good evening. My name is Han Hu. I'm an assistant professor of mechanical engineering at the University of Arkansas. It's such a great honor to chair today's session. Before we start the technical presentation, we'd like to make two announcements. First, so all of our previous lectures and the presentations are recorded. If you would like to access those videos, please send an email to ttc-info@mit.edu. Then they will send you the access to the videos. A second announcement, we will send out a poll for the schedule for the next meeting. Our next speaker will be Dr. Yungjin Wang at UC Irvine. That concludes the announcements. And I would like to introduce today's speaker, Dr. Yutaku-𝗲𝗄𝗧. Dr. 𝗲𝗄𝗧 is an assistant professor of mechanical engineering at the International Institute for Carbon Neutral Energy Research at the Kyushu University, Japan. He joined thermal fluids physics lab at the Kyushu University as a faculty member in 2019. Right after completing his Doctor of Engineering study. Dr. 𝗲𝗄𝗧's research is centered on fundamental problems coupling multi-phase flows, interface phenomena, wetting, and phase change heat transfer, primarily for systems involving nano, macro, millimeter-sized droplets. Today, Dr. 𝗲𝗄𝗧 will present his work on quench mechanisms of spray cooling from single droplet to spray level. Let's welcome Dr. 𝗲𝗄𝗧. Dr. 𝗲𝗄𝗧, the floor is yours. Thank you.
Thank you, Han, for a very kind introduction. So good evening and good morning, everybody. My name is Yutaku-𝗲𝗃𝗃. I'm currently assistant professor at Thermal Physics Laboratory of Kyushu University. So as in the title, I'll be talking about some part of my work on spray cooling. But before I begin this talk, I'd like to introduce a bit about my work, which involves a lot of droplets. Okay, so I finished my PhD in 2019, and my dissertation was about fundamental process of phase change and flow instabilities of drops or droplets. So I love droplets. I just love to see them, and I look up the word droplets on Instagram, for example. You have a bunch of tons of pictures capturing how beautiful they are, and it's not just beautiful, but sometimes it can be useful. So we make use of this so-called coffee ring effect. We can optimize the inkjet printing process or coating process. And if you can control the wetting behavior or flows, we can make a sort of droplet-based devices. So we can make droplets more useful for a particular purpose. So I've been studied many physics problems involved in droplet systems. I'd like to introduce a few of them. So first, I have studied the wetting problem with droplet. So basically, we have fabricated the surface which contains contrast of wettabilities. So basically, we have micropillars here, and we have just stepwise micropillar, the different micropillar patterns. Okay, so if I place a droplet at the boundary between those two different patterns, then see how the droplet moves. So obviously the droplet moves from hydrophobic side to more hydrophilic side. And we closely looked at how the drop walks to the droplet, to the surface which has lower contact angle. And also I have studied the basic mass transfer problem, so basic evaporation process. Okay. Also, I have attempted to control the flow motion within the droplet, using just the principle of Marangoni flows. So basically, I use a point heating source, which is basically laser or micro heater, to generate the temperature distribution as I want. And following the temperature distribution, you can generate the Marangoni flows in a particular direction. So, and this is some of our work, my work that I've done for my PhD. So today I'll be talking about spray cooling. So spray cooling can be used, so it's not a very new technology, is it? So basically spray cooling has been used in steel making process, and also fire safety. So this is sprinkler, and also nuclear safety. And also a mist cooling in town, and as well as micro exit cooling potentially. But I'll be focusing on this particular application, so steel making process. So this is a video of hot rolling process at a steel company. So you can see that this red steel plate, so which means very hot, right? So apparently the temperature of this plate is around 1000 degrees Celsius, and it goes through the line, and you see lots of water spread onto the surface to cool it down. And why we do this is we want to control this thermal history of the plate, so that we can change, or we can control, or we can create some microstructures within the material, which is basically which basically changes the strength of the material. So if you change the cooling profile, you have different microstructures, and you have a desired strength level. And this chart shows a typical cooling profile of this spray cooling process. So if you take the temperature of the material as a function of time, so first, since the temperature of the plate is around 1000 degrees Celsius, so obviously you start with film boiling regime. So film boiling regime generally has poor heat transfer performance. So the temperature decreases like this, and at some point you will have a transition from film boiling to nucleate boiling. And when you have nucleate boiling, the temperature drops rapidly to the saturation temperature, which is about 100 degrees Celsius, and then it goes to the single phase regime. And what's important here is we want to know when this transition happens, okay? Because so once the nucleate boiling occurs, then the thermal history will be pretty much the same, because the heat transfer performance is just dominated by nucleate boiling heat transfer. So it's very important to know how long the film boiling lasts, and when the quenching happens, because this basically determines the whole thermal history, and which determines the final product qualities. Okay, and it has been reported that there are so many influential factors, and these influential factors can be categorized into two. So basically, spray side conditions. So we can play with liquid properties, but basically in industry we use just water. We can play with flow density, droplet diameter, velocity. So these are nozzle properties. And these are okay, so we can control them. If I know how these parameters influence the cooling curve, then we can just change the spray conditions. So that's okay. So what can be tricky though is the target size. So the surface roughness or wettability. So basically, if you have rough surface and more wettable surface, you basically increase the quenching point. So you enhance the quenching, which has been known. And another problem that I'm talking about today is the layer, oxide layers or scale. So So in this slide, I'll be describing how oxide layers influence the cooling curve. So basically, since the steel plate is heated up to several hundreds or 1,000 degrees Celsius, so you have oxidation on the surface. And it has been reported that if you have oxide layer, you will increase the quenching point. So this is the sample with oxide layer. The scale thickness is around 50 microns. You get the quenching point around 400. And if you have thicker oxide layers, then you have much, even higher quenching point. And so this is okay. So you have oxide layer, you enhance quenching. But what is tricky is that you don't have oxidation uniformly on the whole surface, right? So oxidation is something we can't control precisely. So basically, you have this local oxidation on the hot rolled material, and this is just I think this is a thermographic image of the process. So you have this local cold regions. So basically, if you have oxide layers at the random area, and you have faster cooling property on these particular regions, and the rest of it has rather lower cooling properties, cooling performance. So if you have this non-uniform cooling profile over the surface, then then the material will accumulate some residual stress, right? And the residual stress will cause this cracking or some catastrophic failure. So we don't want this. So it is very important to know how this. So even though we can't control where the oxide layer will be developed, but we have to at least assess the risk of it if I know how these oxide layers influence the cooling performance. Okay, so that brings me on to our work. So earlier part of my talk has been published in Applied Thermal Engineering in 2020, so last summer, and most part of my talk basically involves many people. So our master student, so Mr. Inoue, he's just graduating soon, and these two other students are working on experiments and modeling, and also two graduates have worked on this project, and also of course my colleague, basically my seniors, and also industrial partners. Okay. So in order to, so first we study how these oxide layers affect the cooling profiles. We did some spray cooling experiment. So using this kind of setup, so we have a water reservoir, and then the water is pumped up to the nozzle, and from the nozzle the water is sprayed onto the plate. So we have stainless steel plate here, and we coated this stainless steel plate with some oxide materials, and so we have thermocouples embedded here so that we can calculate the surface temperature, not really surface temperature. We obtain the temperature at the interface between this oxide layer and the stainless steel plate, just by solving inverse problem of heat transfer, heat conduction. Okay, so this is some specifications of spray used here. So flow density is around this, and the mean droplet diameter was around 330 microns. Droplet velocity was 10 meters a second, and also we kept the temperature of water at 30 degrees Celsius. And so, and this is a picture of this our setup. And we've tested 5 different samples. So basically, for reference, we had just a bare stainless steel plate, so there's no oxide scales, and we had 4 different compositions of oxide layers. And so so we fabricate this sample not by oxidation, but we actually coated these materials by thermal spray method. So this is how we made the samples, and then we have 5 different and then so we have 5 different thermal properties basically, and these so here I just listed some of important thermophysical properties which I use later for the for further analysis. Okay, and also we've tested 5 different thickness. So from 4 different thickness from 50 microns to 200 microns. And as for the effect of surface roughness, as we've measured, we didn't see much variation of surface roughness. So in this particular study, we have ruled out the effect of the roughness. And also contact angle, we've measured the contact angle at room temperature, and we found the contact angle is about 70 degrees Celsius, and the variation is rather limited. So we have ruled out the effect of contact angle too. Okay, so this is the typical cooling curve we've obtained. Okay, so this is the temperature at this interface between oxide layer and the stainless steel plate as a function of time. So we have a reference line here. So this is the no scale case. So there's no oxide layer. So this is the basic cooling curve for stainless steel plate. And so we can define the quenching points at this. So this line corresponds to film boiling regime, and this steep temperature drop corresponds to nucleate boiling. So the quenching point is here. And as you can see that if you have oxide layers, then you have increased, and we have increased the quenching point. So in this particular case, we had a quenching point just below 300. But if you have oxide layer, you get the quenching point just around 350 and even 400. And the peculiar case here is that when we had a silicon dioxide layer, we didn't actually see the film boiling region at all. So just once we started spray cooling experiment, just temperature dropped rapidly to around 100 degrees Celsius. So we didn't get to define the quenching point in this particular case. And also we found this inconsistent quenching point depending upon the composition of oxide layers. So from this experiment, we've come to a question, right? So the first question we have raised is that inconsistent apparent quenching temperatures. So the quenching temperature varied between 260 and 550 degrees Celsius. Also, it could be even more. It could even higher. Sorry. And so this is the quenching point, quenching temperature we've measured as a function of time. As a function of thickness of oxide layer. So so we increase the oxide layer. If we increase the oxide layer thickness, then you will have a slightly higher quenching point as reported previously. But okay, so if you compare this quenching point among these different oxide layers, then you have this variation of quenching point. So that's something we didn't understand at this moment. And also, if we can think about the thermodynamic limit of superheat of water, which is around 300 degrees Celsius. So this quenching point appearing at this very high temperature didn't seem to make very much sense. So there's another question. So are we violating thermodynamics here? So these 2 questions that I will be addressing later by looking at fundamental process of spray cooling, which is droplet impact. So we've done the secondary experiment on single droplet impingement. This is the setup. So we have a cylinder of stainless steel, and we have embedded the thermocouples here, and the stainless cylinder is heated using the heater. And we have a tiny nozzle. So this is called microjet dispenser, which can just eject one single droplet, and we can precisely control the diameter of the droplet and the velocity of the droplet, and also the temperature. So we can just focus on one single droplet as a fundamental process of spray cooling. And in this particular experiment, we just limit the Weber number as around 20. So, but in reality, we have a wide range of Weber number, but we just limit this number so it makes easier to analyze. So from this experiment, we have looked at two different droplet behavior, which is behavior, and also depending on the temperature range, we had two different droplet behavior. So if you have basically higher temperature, we have observed bouncing droplet. So which is basically because film boiling regime. And if you lower the temperature, then the bouncing regime ends, and then the droplet just stayed in contact on the surface until it evaporates away. So we classified the droplet behavior into two regimes, and we measured the maximum droplet spraying diameter as well as the contact time. So that this is the so we measure these two parameters as a characteristic of droplet behavior. So and also we've done some calculation based on the elastic model of the droplet bouncing. So this can be used as a reference. So this is the contact time of droplet contact time as predicted by the elastic bouncing model. So this basically assumes there's no liquid solid contact. Okay, so this corresponds to film boiling regime. So if we have, in film boiling regime, we should have the contact time something around this value. Okay. So if I normalize our experimental contact time by this value, then this value. So when we get this value close to 1, which means we have a film boiling regime. So this is just a useful reference value. Okay, so this is the chart. I plot the normalized contact time as a function of wall temperature. So so this normalized contact time. So here I draw the dashed line corresponding to the normalized contact time of 1. So if I had data somewhere around here, which means we had a very minimum liquid vapor, so liquid solid contact. Okay, so from this figure, if you just focus on one particular case, so this, if you look at this, let's see, so green data, green triangular data, if you have a higher wall temperature, then you will have shorter contact time because you have film boiling regime. And if you lower the temperature, then you get the longer contact time because the droplet stayed in contact with the surface. But overall, if you see this, if you want to compare this behavior among these different oxide layers, it doesn't seem to make very much sense. So so we didn't get to find why this transition happens from this figure. Oh, sorry, I should have shown this video. So at higher temperature, we have this bouncing regime, and lower temperature, we have this, boiling or evaporation regime. And also, as also this, like the spray cooling experiment, we had a particular data, particular case for silicon dioxide. So we didn't have bouncing regime at all in our experimental range. And we also did the same experiment for different layer thickness, and we didn't get much insight out of these figures. Also, if I plot the maximum spring ratio, so this is the maximum spring diameter divided by the initial diameter of the droplet. We have this nice curve here, but still the transition from film boiling regime or bouncing regime or deposition regime are not very consistent among these oxide layers. And the same can be said for different layer thickness. So from these figures, we had a problem with this wall temperature here. So because so from this experiment, we thought that this wall temperature doesn't represent or doesn't explain what and why this transition happens. So we have to define something else. Okay, so we defined a so-called contact surface temperature, which can be calculated by transient heat conduction analysis. So this is just a basic case. So basically, the contact of two semi-finite bodies, and from this this model, we can get the surface contact temperature, which is somewhere around here, by using just these parameters that we know. So we know the wall temperature, and we know the droplet temperature, and we know the thermal properties of the sample and the droplet, right? And so this means that we have so when these two bodies, so droplet and the wall, comes in contact, you have a temperature drop from the wall, and the temperature increase from the liquid. So the interface, this temperature meet where this temperature profile meets, we have this interfacial temperature. So this is so here we list. Here I list some thermal properties of oxide layers. So you have a wide range, big variation of these parameters. And in right-hand side, I plotted the contact surface temperature calculated by this model as a function of wall temperature. So so to see how much gap we have from between the two. Okay, so if you have rather high thermal properties parameters, we don't have much gap between those two. So if you take the 420 degrees Celsius of wall temperature, actually, so then the contact surface temperature will be somewhere around 300, yeah, just below 400. Okay, but if you have an oxide layer material which has very poor property here, lower value of this property, you will have a huge temperature drop. So if you take 420 degrees Celsius again, then actually you have a contact surface temperature of 250 or something like that. So there's a big gap between those two temperatures. Okay, so so then I have replotted the normalized contact time and also maximum spring ratio as a function of newly defined contact surface temperature. And now this the data plot shifted toward the left, so lower temperature region. And now you see the clear trend, clear transition from between the two different regimes, both in the contact time and the spring ratio. And regardless of the types of oxide layers or thickness, we had consistently the transition at about 250 degrees Celsius. So this could mean something. Okay, so we had some outlier here, but we actually associated this behavior as bouncing regime, because if you look at this video, you see the bouncing droplet wants to bounce off the surface, but actually there's some local variation of temperature or roughness. The droplet stayed in contact in a very local area, so that you know, that we ended up with rather high contact time, but still this is bouncing regime. Okay, so also we've tested the effect of droplet temperature, and you know, it didn't really matter in terms of the transition of droplet behavior. But what it tells is that if you have a higher temperature, then you eventually have higher apparent quenching point, because you know the surface contact temperature is dragged toward the higher temperature if you have hotter droplet, if that makes sense. Okay. So then I'd like to move on to the modeling of cooling curve. So now from our experiment, it's still a single droplet impingement experiment, not exactly spray cooling, but from our experiment, we can infer that quenching is likely to happen when the surface contact temperature is about 250 degrees Celsius. There's still question why 250, but just we leave it there. The next problem is that how fast does this temperature reaches 250 in spray cooling? So we want to know how this slope, how this temperature changes and reach there. So so basically we want to model the film boiling cooling performance in spray cooling. Okay, so we did some computation, or we developed some model. So I'd like to show some of it. Okay, so we consider a simple case scenario. So we have just a one direction transient heat conduction problem in the plate. So this is the plate. So this is the model of the plate, and so we have to. So this is just simple one-dimensional heat conduction, and we have to give two boundary conditions. The one is adiabatic condition at the end of the plate, and from the surface where the water is splayed, we have to give some sort of heat flux. So how do we model this heat flux? So we can estimate the heat removed by each droplet by a particular model. So we use this kind of model to estimate how much heat is removed by the droplet. So the unit will be like this, the joule per droplet. And we can multiply this by the number of droplets in a unit area and unit time. So this is basically spray condition. So we can give it. Okay. So if you multiply these two parameters, then we can get the heat flux at the surface. Okay. So as for heat transfer through the vapor film, so vapor film, we follow the analysis by the French group, which is published in 2018. So we have this schematic model. So the droplet is floating on the vapor film, and heat from the wall. Some of the heat will be transferred to the droplet, and some of it transferred to the vapor. And the heat transferred to the droplet, which is denoted as QL, some of is partially used to evaporate, right? For evaporation. So the heat goes like this. So we have heat balance equation. We can make a heat balance equation considering this. And also, since the vapor layer, it should be much thinner than the droplet size, so we can apply the lubrication theory. So then we model the flow motion inside the vapor layer. Basically, we assume Poto flows and the mass conservation and also heat balance, as I explained now, and the momentum balance. Basically, so droplet. So we have to calculate the pressure in the vapor film such that it can lift the droplet, keep lifting the droplet. Okay. And also heat transfer inside droplet should be calculated. And from this submodels, we can eventually get the wall heat flux. So the heat flux is basically heat conduction through the vapor film. So this is okay. And what we have to know is that the thickness of the vapor layer. So vapor layer, since the vapor layer film grows as function of time. So we can estimate the vapor layer like this. And this is the sum of calculation we've done. So on the left-hand side, we plot the vapor thickness as function of time. And also from the vapor thickness, we can also calculate the heat flux as function of time. So which should look like this. And to get the amount of heat taken by the droplet, we have to multiply this heat flux by droplet base area, so which is heat transfer area. So from experimental observation, we know that the droplet base area changes as a parabolic function of time. So we can use model the droplet base area like this. So if you multiply these two and integrate it over the time, then we get the joule, the amount of heat in the unit of joule. Okay. So this is how we model the heat transfer through the vapor layer to give the boundary layer, boundary condition of this 1D heat transfer problem. So this is the computation procedure. It's not that complicated, I guess. So first we have to set the initial temperature profile in the plate, and then we give this boundary condition of heat flux, which we can determine by the model that I presented earlier, and then solve the 1D transient heat conduction problem, and then get the new temperature profile. And then we set the temperature and using this new temperature profile to set the new initial condition, and then we repeat this calculation until the surface temperature reaches 250 degrees Celsius. Okay, so this is just recently we got it done, and we now I plot this temperature profile as a function of time. So as for reference, I plotted here in the black line. This is a cooling curve obtained by our experiment. Okay. And this red curve is the cooling curve predicted by our model, just I presented. Okay, so this seems to be, it doesn't look very bad, right? So so cooling rate is on the similar order of magnitude, so that's okay. But still, the cooling rate looks a bit slower than the actual data. And also we have this blue curve here. So this is a heat transfer calculated. So this is using so-called wetting model. So this wetting model assumes basically there's no film layer between the droplet and the substrate. So this is just complete, direct heat conduction from the surface to the droplet. So these two are basically two different extreme cases. And if I look at this figure, I can infer that in reality, as in the experimental curve here, that we have just two combined heat transfer mechanisms. So most of the droplet are floating on the film, on vapor film. So it has film boiling heat transfer, but some of the droplet, some of the region of the droplet may be in contact with the surface. So it may make sense that the actual cooling curve should be somewhere in between those two curves. Okay, but we haven't actually optimized the calculation procedures or grid size or time intervals. So we shouldn't rush into this conclusion. But so far this is our idea. Also, since we had difficult time, so we have some limitation in laboratory work. So we decided to do some CFD modeling. So we used ANSYS Fluent to solve VOF model of the droplet. So we have this schematics as a model of calculation. So we have a standard split heated up to 400 degrees Celsius, and we have a droplet here. And you can see the boundary condition, something like this. And this is the actual mesh or grid that we used. And the initial temperature profile is set by natural convection. So we calculate this temperature profile before we induce droplet impingement. And also we set the contact angle as 180 degrees Celsius so that we can sort of simulate film boiling regime. It's not completely realistic, but I wanted to just see how the droplet behaves on the surface in film boiling regime. And obviously we have some difficulty in modeling phase change problem. So we have no phase change here. Okay, so this is the calculation result. So which looks like this. So on the left-hand side, we just temperature range is set so that we can focus on the temperature variation of the substrate. And on the right-hand side, we change the temperature range so that we can see the temperature variation of the droplet. Okay, so the droplet behavior looks okay if I compare it with the experiment. And also the temperature variation seems reasonable. So that the temperature, sorry, I couldn't say reasonable because this is not a very realistic model, but we can actually quantify the temperature variation within the substrate. Okay, and also from this data calculation, we estimated the heat taken by the droplet. And we had this value, so 6 millijoule per droplet. And from the vapor layer model that I presented earlier, we had actually the heat removed by droplet is around 0.2 millijoules. And from the experiment, we also obtained the rough estimation of heat transfer by droplet is around 1 millijoule. So I would say they are not very too far from each other, but the experiment, experimental data was somewhere between the two. So just my idea being that there's a combination heat transfer mechanism in real spray cooling might stand but just I'm not very sure. So I'd like to ask you. I'd like to. I'm very welcome to hear your thoughts. Okay, so I have talked too much today, but this is basic conclusions of my talk. So I have shown you two different experiments. So from a spray cooling test, I have pointed out that there's a huge impact by the oxide layer on quenching temperature. So we have inconstant apparent quenching temperatures. Also, the cooling rate are different for different oxide layers. And to see why this happens, we did a droplet impinging test, and we found that quenching might occur at the surface contact temperature of around 250 degrees Celsius. But the question remains, why 250? And that's something we have been working on right now. But if you have any idea, please share with us. And also, we've been doing some modeling, which is underway. And I wanted to show you some of our progress today. So thank you very much. When the situation becomes normal back again, I'd like you to visit our campus, which is just huge and in a very nice place in Fukuoka. So visit us. Thank you very much.